Hello, everyone. I'm coming from UC Berkeley with a joint appointment in the Department of Civil and Environmental Engineering and Urban Planning. Today, I'm going to present to you how to do planning and modeling of urban systems using novel data sources. I'm going to present two papers. The first one was published in 2019, it's available online, and the title is Planning for Sustainable Cities by Estimating Building Occupancy with Mobile Phones. It's an interdisciplinary work that has people from architecture, the Department of Architecture at MIT, and my group that was transitioning from civil engineering at MIT and now in civil engineering and urban planning at UC Berkeley. The aim is that most of the work using mobile phones has been for traffic and mobility. And when people is not moving, they are staying. Most of the time they are staying in buildings. And our aim, this is the first attempt to use mobile phone data for a different purpose, not to see how we occupy the streets, but how we occupy the buildings. To that purpose, we model 3.5 million people in the greater Boston area. And we do a framework, a proposed framework to estimate how buildings are occupied. So for this part of the talk, I'm going to show you what are urban building energy models about, how we use the TimeGeo Modeling framework, which use mobile phone data to estimate building occupancy, and then the implications of the results in the case study of Boston, of the Boston metro area. So first and all, the motivation to reduce CO2 emissions. A lot of effort has been done in transportation, particularly because the transportation industry has become autonomous, electric, and shared. Due to these changes, it's estimated that the share of CO2 produced by transportation is going to, hopefully, to reduce. However, in the building area, the trend of reduction is slower, and it has a lot of impact. So the main motivation of this work is how we inject the power of ICT, information and communication technologies, into the building occupancy planning. And to estimate how buildings consume energy, it has a component that is based on the construction geometry and weather that is going to determine what is the use of heating and air conditioning, basically. And there is another component that takes human factors, that is, how many people are in the buildings, and once they are in the building, how they are using the different sources of energy. Mostly, you can think that when people is in buildings, 47%, almost 50% is due to heating. And the rest goes into cooking, hot water, appliances, lighting, and air conditioning. So basically, HVAC is about 50% of the consumption. Then we need to know when the people is in the residential areas or the commercial areas, and then break down their uses. Occupancy is one initial factor that hasn't been informed by information and communication technologies. Let me tell you about the typical data sources to study occupancy. Are these smartphone data or location-based services is one option, and the other are triangulated signal of mobile phone users. Here I'm showing as a benchmark the sensible DTU from Danish Technical University of Denmark. This is a snapshot of how the collected data of smartphone users look like. The model we used to get occupancy from mobile phone is the so-called TimeGeo model that was published in PNAS in 2016. And basically, we parse trajectories to divide the cloud of points that a mobile phone user gives you in stay locations and mobility. And the main challenge is how to complete the locations where we don't have data from the users. And basically, we classify the stays in return to already visited location or to exploration, and we created a framework to model when, a probabilistic framework to model when a person is going to move, and if it's going to move, if it's going to be an exploration, to allocate an exploration. So it's a mix of collective behavior, statistical patterns that makes differences between the individuals, and some aspects, some ratios that are from individual mobility patterns. This is just to give you a flavor that is a purely statistical model that completes the location of individuals based on where you most likely see them in the city of a story. To this audience, I would like to mention when we model someone, a lot of the efforts in computer science has been on where the person is going to be. However, 70% of the visited locations are explorations, meaning they are observed only once. Then here we have a smartphone user that we use the framework from the previous slide to complete it. And we see that about 46% of the time, of 363 days of one person, we don't predict the location properly. So depending on the day, we have from 80% to 46% accuracy in the prediction. However, this is beyond having exactly where the person is or knowing where the person is in a given time. I'm going to show you for urban planning what are the aspects that we are more interested to predict correctly. And it's about the patterns. The patterns are how many daily visited locations so a person does in a day, and of course it's a distribution. And then we want to predict that ratio correctly. We want to predict how long the person stay in one of these visited locations. And very importantly, I mentioned that you can have a visits a location only one. Those are the ranked large ranks. You have a few fraction of time you visit them, and the first few ranks you visit a lot. Here is the fraction of times a person visits a location of rank L and is of this type. Then you want to know not only how many locations a person visits in a day, but model the rank properly. And of course, as a byproduct of this, you have the distribution of distance traveled properly done. So basically, you get data that is sparse in time, in space and time, so it's incomplete, and we model every 10 minutes where the location is using aspects of their visitation. And by modeling somebody, we have these patterns properly. That matches well where the person work, live, the places he visits a lot, and the places where he or she may be found doing an exploration. And we do this for every mobile phone user. This talk is about how to use this framework of a sample user. Here is a location-based service usage of cubic, how we do the stays, how we complete the stays, and how we use this framework to model entire population in a city, and then to estimate building occupancy. One aspect I want to show in terms of the universality of these models, in the left-hand side, I show the sensible DTU patterns to complete the trajectories, the distributions. And in the right-hand side, I use triangulated data from EarthSage, which the distribution looks similar but cleaner because it's hundreds of thousands of users, and in the other we have hundreds of users that are students. If you have only students, the rates of mobility, exploration, and return and stays is different than the entire population. But they are centered and they have a order of magnitude that are similar. So the distribution have similar shapes. Then as a result, we have for the users that have very few records, like this one in the left, we can use the distribution shown in the previous slide, and we can model people. So the users that are not very active, we complete them. These are the sparse data. We complete them with the distributions we train with active users. And in this example, we can have this realization or this realization, and they are a different type of model users. Then, when we aggregate the travels and we compare these whole details record, home, work, camper flows with the commuting transportation planning package, the flows commuting is very good. When we assign these informed models with mobile phone data into the streets, we are very effective modeling road usage or traffic, because we are feeding our flows, number of trips from origin to destination, or ODs, with a lot of users. In contrast, what the transportation community had to create these models was 30,000 users for the same Boston area. Then the first revolution of this data was into transportation models or human mobility models that my group and other groups has done for several years, for the last 10 years or so. However, much less has been done to apply these models into the building occupancy realm. And this is exactly what we want to do. After we parse the trajectories, we complete them, still, we do not observe one mobile phone provider with all the users. And for building occupancy or travel demand, we need to have an estimate of everybody. For example, the CDR data that we have from Boston is 1.92 million people, but we want to model 3.5 total population in the Boston metro area. To that regard, we extracted these rates of mobility, and we need to expand the users. Meaning the expansion factor is the ratio between users we have and total population. And it's peaked in 23 in the case of Boston. That is, we have, for every mobile phone user we observe, we're gonna model 23 with these mobility patterns. As you see, the places where we have this tail, hundreds of users, 100 of people per individual user is in the suburbs. So this is the framework. We have the model, and we have like a video game in which people is moving. A big fraction of them are real users, and a few of them are simulated based on census, but they behave similar to their to the users we observe with the same heterogeneity. With that done, let's go into the building realm. So we are going to consider not the greater metro area. We are going to go into the city of Boston. The city of Boston have 82,000 buildings, and they are classified by different types. You have all the different type of residential, from apartment to single occupancy houses to mixed use, commercial, industrial, and so on. So here by colors, all these at the beginning, the majority are residentials, and then we have all others that belong to commercial and industrial. We have the typical classification and their schema. So that is their footprint with their actual size. Then when we do inside Boston, just for illustrative purposes, I'm gonna go to one neighborhood that is called Back Bay. And here we have in a weekday, the stays of 21,000 people that are in this small area with 414 buildings. Notice the heat map where the stays are. The main challenge is that, similar as when we did the route assignment, the phone data never tells you the exact route people use, not the whole detailed records. But they tell you the triangulated location of the antennas that give the communication. Then all this that you see in orange is a combination of having more people around there, but also the location of the antenna. Then the main component of this is that we need to do a probabilistic estimate. We know how many people is in the area, and we need to distribute them in a smart way that is going to give you the probability that a certain amount of people is in a given place, which is in this case a building by time. This is not a matching problem. This is a probabilistic estimate, the challenge. To do so, we use data. We use point of interest. We use the schedules of hours of operation in the case of commercial places. As those of you that have worked with point of interest data, you know that a same place, let's say here a cafe, can have different type of labels. Then basically we simplify the point of interest label with one use of the building. Then we have a school, university is one label. We use school use and that type of matching. We simplify the labeling. We use the hours of operations from the point of interest. And we use area per person, person capacity area. So basically values, we know that buildings can have a certain amount of people per capacity area. Because we have the building, we use from the point of interest, we assign to each of our buildings a given amount of people that they can receive. Then we need to deal with the actual challenge of the data, that is our stays cover an entire region. This is an example of several buildings, that hundreds of buildings that could receive stays that are around them. Here we have one person that is staying here, and we want to come with a way on how to distribute it. And we need to do that for each of the stays are in different regions. Then we know from the users if they are at home, work, or other type of stay. And then, of course, if the person is at home stay, we're going to only assign them in the residential type of buildings. Work can be in commercial, industrial, and other can be in commercial. Then, here is the main hypothesis that so the main creation we did, and it worked. And it turns out that we do a clustering algorithm to group buildings according to a walkable distance. So if we have several buildings, we group them, and then we are going to attract the people of the mobile phones in the States to the different group of buildings. In this example, we have 400 buildings, and then we have cluster of 52, 23, 13, 50, and 41. And the assignment of the different clusters is proportional to the capacity of the cluster times the capacity at a non-linear exponent. What this does is the attraction is not proportional to the actual capacity, but a number that is less than 1. What this gives is that the number of people that the building is going to attract is proportional to the actual space available, but not completely. Otherwise, the bigger buildings are going to attract everybody. So we at the beginning found this empirically, that it worked in a reasonable way, which was 1/2. And then the referees asked us to go into fine-tuning values of this exponent. So in this selected example, we would assign the person to one building, to one cluster, and then to one building, and then we add, and we do that for all the mobile phone users. And then we can see how it works, because basically we have two temporal aspects that work here: how people move, and the capacity of the building, is they're open or closed. And then what we show here is that the total occupancy from phone data of the commercial buildings follow this red curve, and the residential building follow this curve. And we have the 20-something stays are distributed in this nice circadian pattern. And I'm showing you this block of buildings, and we do that with all the phone data, with all the buildings in the Boston area. Now, let's do a little bit of the analysis on basically. Now the big question is how we validate our framework, and how it compares of how things are done, and what is the impact of this framework. So first things, let's see, we observed that the maximum occupancy of the residential buildings based on the phone data, so the empirical occupancy versus the maximum occupancy, we see that residential buildings have more people than the maximum nominal for, let's say, a single family occupancy and different apartment occupancy. There are estimates in the energy manuals that give you the maximum capacity. And then we see that with this data, we are assigning sometimes 3, 4, 5 more in residential places. While what the manual has for commercial building versus the actual people we see, we are assigning less than 50%. So there is a mismatch between what is the maximum capacity that the energy simulations have versus our assign. That is a general framework. But we also show there was a total distribution in the buildings, that the buildings can be divided. So you show here, I show you before the curve by residential and the typical curve by commercial in the lower part, but we don't have only one type of residential, and that is kind of neat. We have a cluster 1 that is about 20% of them that are flat, people that do not live them. Then we have the typical that is about 45% of them, that is they're occupied at night, then half occupancy in the day, and then back in the evening. And we have this cluster 3 that really are low occupancy during the day. Similar happened with commercial buildings. So nicely, we have buildings and different ways in which they are occupied in this new type of model that is not for traffic purposes, but for building occupancy. And now comes the real challenge, that is how we validate what we are proposing. And for that is that we did this because we were having this interdisciplinary collaboration with the Sustainable Design Lab from MIT, that they have an urban building energy model from Boston. And there are several papers on this. Basically, they have the exact geometry of buildings. They use Energy Plus, in which they use the manual capacity, and the rest is the standard way to model, given this manual amount of people, the amount of people in a place by the manual, how they are going to consume. And that is a model that depends, given this amount of people at a given time, they may be using water, electricity, heating, etc. So the Energy Plus is the software standard in the United States to do this, and is developed by the Lawrence Berkeley National Lab, funded by DOE. And the SDL, those Rhino and some aspects of the front end of this simulation. So basically, how the result of the SDL Boston energy model would be not using mobile phone data and using the occupancies we provide. What are the differences? What are the implications? What is better? So the SDL, these type of things, that is the archetype, meaning the details of the buildings. They give you the 3D model, they take into account the shading, they do the Energy Plus simulation and the results. What we are going to have them is running them with and without the phone data to show the differences. And we're gonna do this for 1,200 reference buildings using this occupancy. And the type of buildings are single use, multi-use, and they include residential, retail, so it's a whole mix of uses, as you see. We use a particular area in which not all have the same, so basically we have a very mixed and complex type of use. And here is the big result. When we use the number of people in buildings at different times of the day, and we show the census population, of course, it doesn't change across the day, and we see the mobile phone occupancy that we observe in the area. You see the light blue line versus red. And what the Energy Plus nowadays use is this Department of Energy reference building use is by manual, by construction, is 4 times higher. So already they are assuming there is way more people because they are not even using census, they're using the capacity alone, versus what we distributed were actual users modeled, and then our amount of people occupying buildings that we're using as an input is way different, is 4 times different. And the flux is not too different. We have the flux that the DOE number of people moving, and we have the number of people with the mobile phone user versus DOE. And we have the hourly occupancy, the difference between this is a distribution that tells me the difference. Okay, here I'm showing the total difference by hour, and here we're showing the difference building by building. So it's not that in one building we did it completely different. So in general, we have a whole distribution in which, on average, in the residential areas, the DOE is predicting around 8 times, eight more people than what we model with the demand model of phone users. And for the building, it's much more. So this is, in every single building, you have between 10 to 10,000 more people estimated by the manual than actual people there in the model phone data. And in the residential parts, per each person, the DOE is assuming 8. Then when we see this building by building, here is a typical residential building. So we took apartment 1, apartment 2, and then we were seeing the different curves that are the occupancy curve. And here we have a typical apartment 2 that we have the much more occupancy by DOE. And always is, most of the cases is more, and this is how it's translated in occupancy building by building. And now the detail is that once we know the occupancy, there are other aspects to model the energy. The occupancy is one thing, and then based on the occupancy, it is known that how much light is going to be used per person, how much hot water, what's going to be the gas, and all the different sources. Then we want to do the occupancy, introduce the impact of that into the energy plus in 2 ways. The one that we call a high impact is we do not use the previous occupancy, we just use the new and we see how much it is, the new use of energy. And in the other, what we call the low impact occupancy, what we do is basically we use the first one and we use only the shape of our new occupancy form and we use the totals that were before. So basically, these are 2 scenarios to assume the actual new and offering the second estimate that can be more between the new and the old. And now we have here, based on 2, an apartment and a mall with the with different occupancies, what would be the use of lighting, equipment, which is appliances, and hot water. When we do the high impact, so the new occupancies, you have the rod curve, we see that is in general using less of everything. And when we have the low impact, this is a scenario 2, that is only doing the normalization, we see that is less dramatic, the impact. Overall, when we estimate the impact or energy saving of different measurements, energy measurements, we have the reference base, the low impact, high impact estimates. We see that the estimates are affected by this new metric. So basically, this is a reference, this is a low, and this is the high, and then we can see how much electricity we're going to save, how much gas, how much total we're going to save. And in general, we can see, for example, that the difference between an equipment upgrade, saving estimate, using the new occupancy can be saving of 4%, while if we use the DOE reference case, we're going to be saving only 3%. At the end of the day, if we want to see the impact of energy metrics, we need to have good occupancies. The occupancy of DOE is off by several order of magnitudes. The impact on the energy use is not that much because the use is not directly proportional to the number of people. Then in conclusion, we have demonstrated novel method using phone data and other data sources to get a city-scale building occupancy. Our results indicate the commercial buildings operate under capacity, large neighborhood variation for residential buildings in terms of occupancy. This lack of use of ICT for occupancy give mispredictions and highlights the need of new data sources beyond the manual to estimate building occupancies. With that, I would like to go to the second and last topic of this talk, that is how we understand the laws of facility distribution in cities. Is impressed in Science Advance, is available in the archives. So the motivation was by this paper of 2006 by Mark Newman, and in the entire 8 million blocks, so we have the population in the US at the block level, we have 8 million block levels, blocks with population, and we need to distribute 5,000 facilities. If we want that the distance to the population is minimized, how these facilities would be distributed. And here is the result of these 5,000 facilities distributed. And the resolution of this optimization problem is that you are going to put the facilities in a given place proportional to the density of population of that service area, but not just linear, not linearly. So is the density of facilities is distributed in a space as a population density to the 2/3. That would allow us to have access, minimize the access of the entire population to the facilities. Interestingly, a follow-up study in PNAS in 2009 showed that if what we want is that the facilities get the major number of each facility is commercially driven, and we want them to get the major number of people, then we need to have a proportional distribution. So empirically, they show that with data from Korea, South Korea, they show that facilities such as hospitals would be to the power of proportional to the population, and facilities such as public school were more to the 2/3. So basically, it was postulated before our work that facilities to be distributed optimally, you only need to know the density of population and how to put them in space. We were very interested in how to distribute, not at the country scale, but in a given city, to explore if these laws remain, and we wanted to show differences in the accessibility and distribution of facilities of cities in the world. To that end, we use the ROD network, the land scan population distribution that is at we know how many people there are at 1 kilometer by 1 kilometer cells, and we have the number of facilities by type using the check-in of Foursquare for several years. Then we have these 3 layers of data set, and we're going to compare several cities around the world. We compare here for you to show, to have an idea, Boston, Los Angeles, and New York, we three very different cities from the Middle East that are Doha, Dubai, and Riyadh. Here we see how is the population from the central business district, how the population is differently distributed. And we know also what is the number of facilities per square kilometers also as a distance from the city center. Then we see nicely that the number of facilities follow the population, and we want to explore further difference between them. One aspect we did is how to differentiate the actual distribution of facilities as they are versus the optimal distribution. Then remember, we have different nodes are the locations with given population, and we always have less facilities to distribute than blocks with population. And then we want to compare the distance of the different blocks to a facility place, and each facility has its own service community. So we want to be analyzing what's the difference between the actual distribution and the optimal distribution of facilities. Let me tell you about the optimal distribution. We did this Resende and Wernick optimization problem using Gurobi. And what we do is that we have a set that is a block, a set Y, that is the facilities to be distributed. And we have the cost, and the cost is the distance through the road network. And all the blocks are going to have one facility that is the one that is the closest. And then we calculate the actual distribution, we move them, and we should until we optimize the distribution of those facilities. Then, to give an example, with Boston, we have the service communities of hospitals. In the left-hand side, here is the actual, and in the right-hand side, we have the optimal, and we can always have the ratio of the travel distance in the optimal scenario versus the actual scenario. When we do the log of that, we have that in the case of the red cases are the one in which the actual scenario is not benefiting them. So basically, for the given number of facilities we have, all these red places could be doing better. And the green areas are those that are much better with the actual situation than the optimal. At the end of the day is a social good problem in which we have limited number of facilities to distribute. Some people benefit with the actual distribution, some people is affected by that. What we want to do is to understand the different urban forms and the ability to have the optimal distribution of facilities. For that purpose, we use 4 or several toy cities and actual cities. And what we observe first and all is that in the real empirical distribution, we do not see the power law that was seen at the country diluted case. And here we see when the number of facilities versus the number of occupied blocks of population is very low. We call this the diluted case. And in these cases, we have the 2/3 exponent, while when we have this threshold higher than 10%, we see that this exponent is not observed, neither for the actual cities nor for the toy cities. So that was the first aspect. We did not see at the city scale, we have less blocks, more facilities to distribute, and then the optimization problem the condition is not fulfilled. And then that asks us for how to better study this aspect, given that the power law was not withholding. Again, what we want to do is to model what is the average distance given a number of facilities, what is the average distance that we are going to observe. And basically, it's simple if we can have that the distance is two aspects. L-min is the size of one cell. You have two types of blocks, those that have a facility on it and those that do not have a facility on it. Then we have PJ is then the fraction of facilities that fraction of blocks that have a facility on it, and we want to model the number of facilities that do not have a facility on it. Because it is an optimization problem, we were able to show that the number of blocks without facility decays with n, where n is the number of facilities to be distributed. And then we have an exponential decay with n, and an alpha depends on which city we're talking about. Then when we see C and D, we have the different cities, toy cities, and in the lower left part, we have real cities. Interestingly, what we can see is that as cities become higher urban centrality, meaning become more monocentric, the distance decreases. The average distance of a number n of facilities. Then we can be distributing 10 facilities total, let's say in Dublin versus 10 facilities in Paris. And in Dublin, the average distance to the same 10 facilities is going to be much lower, because Dublin is equivalent to have much more monocentricity than would have Paris. It's interesting to see the similarity in the curve and the fact that given this alpha that can be measured empirically, when we, instead of plotting Ln, we plot L as a function of alpha n, all the results collapse. This is the result of distributing facilities optimally in space. What we can use this very interesting finding for, then we can say, okay, let me fix the average distance I want to reach, and let me discover, given the actual distribution of facility, how many of population, how many facilities I need. And for that, we just need to invert. We fix L, and then we invert how many N we need. Here is an example, for example, to have a distance of 5 kilometers on average to a given facility. We have, let's say, we need 10 of them in Barcelona, but we need 4 times more. We need 40 of them in LA. So this is the difference between having a more dense, condensed city versus LA. In this case, we do not need to do any optimization problem. We do not need any data. We only need the functions we discovered. So the conclusions are that the simple power law does not hold in empirical data for distribution of facilities. In the optimal scenario, the power law requires very small facility density. The optimal travel distance to facility can be modeled as a function of the number of facilities, only knowing the population distribution. And we can estimate the number of facilities needed for a target accessibility, again, only knowing the distribution of facilities. So I hope I show you that we can use data science for several applications that include mobility, energy, environment, and the use of information and communication technologies. And with that, I would like to open the time for questions. Thank you very much.